So good afternoon, I'm Roel Standaert and I work at MWeb, mostly on Witty. I'm going to talk about how we dropped C++03 supports in Witty 4 and migrated to C++11 and modernized it a bit. Of course, this is the decisions we made and the considerations that we made, so I'm not telling you that this is the definite way that you should port every widget-based web framework in C++ to C++11, but here goes. So first of all, to introduce Witty a bit, it was first released in 2006, so it's been around for a while. It was created by Koen de Vosje when he decided that he needed a web interface for this thing he was making, and he didn't like web technologies because for the most part web technologies are, they started out as something made to display pages of information with links in between them distributed over a network, but not really for these single page, very interactive web applications. So he developed a framework that was more like desktop GUI framework, in particular a lot more like Qt. And as a result, we can actually apply graceful degradation to our framework. So when you can actually use a text-based browser to browse a Witty site, or you can use modern browsers and it will use whatever technology is available. And like Qt, Witty has an equally cutesy name. WT is definitely pronounced Witty. So its use is mostly as embedded applications or the front end for just any C++-based application. Usually the kind of applications that have to do a lot of computation in the background, and you need a front end for that. And Witty is very convenient for that. And it's mostly appealing to people who already know Qt and want to port that to the web, because there are benefits to deploying things on the web rather than having it as a desktop application. So to give you an example of what a typical Witty 3 application would look like, you would, in your main function, you would call wrun, which is this utility function which spawns off a server based on the arguments that you pass in, and then you pass in this callback, create application, for example, and that one gets called every time there's a new user who serves to this web page. So every new user session is one instance of a W application. So this W application, this create application gets an environment which tells it something about the user that's accessing it, the stuff like the user agent, IP address, that kind of stuff. And then you make a new W application. This is Witty 3, so you use new still. And then you get like the roots of this application, which is like, in Witty, everything is organized in this widget tree. So you start from the roots and you add everything to this root widget. So this ... that's where you would add a whole bunch of stuff to this root widget and connect your signals and slots, and then eventually you return this application to Witty and Witty will take it from there. So for example, what you could do in this ... is you could get this container, this root in HTML, that would be a div. And then you can use add widgets to add stuff to it. So you create like a button with new W push button. You would give it a name and then call add widget to add it. And you could do the same thing for some text. If you know HTML, that's kind of like a span. And you could have it say button not clicked yet, for example. And then you can take some signals. For example, there's a clicked signal defined on the button, and you can connect that to, for example, a lambda. And so you can update the text when you click on the button. And as a result, it's exactly what you would expect. You see a button with some text, button not clicked yet, and you click the button, and it turns into button clicked. So with Witty 4, what we wanted to do was make using Witty a lot more fun. And for us, that meant making it more clear and more safe, especially the way that we handle memory in Witty. And we wanted to improve our compilation speeds because, well, C++ is notoriously slow to compile. And we wanted to make it a bit more familiar to people who are already familiar with modern C++ 11 practices. So they'd expect to see stuff like, well, a unique pointer owns something and a raw pointer doesn't own it. That's not something in Witty 3, and we wanted to move towards that. And we also wanted to fix a bunch of problems in the API. That's major version increments allow us to do that. But overall, we wanted to keep it consistent with how it already was in Witty 3. We don't want to annoy our existing users by just changing everything and making it completely unfamiliar. And whenever we broke something, we would make sure that if it was a major thing, we would break it at compile time so that users wouldn't, well, be able to just recompile their Witty 3 code and just have a whole bunch of runtime errors, because that would also just be really annoying. So the first problem that we really wanted to tackle is this non-obvious memory management. And this question showed up on Stack Overflow like a week ago. And someone asking the same thing I asked when I started working at MWeb 3.5 years ago. I didn't know that much of C++ yet, and I actually started out with C++ 11 and then had to learn C++ 03 stuff. And for me, it was also weird that I was seeing all these new calls and then no deletes, and I was like, oh, I was really paranoid about, well, where was all this memory going? Is it just leaking everywhere? Well, not really, but the way that we did it in Witty 3 is just whenever you call add widget, that would transfer the ownership to that container. But so the problem with the typical Witty 3 code is, one, whatever happens between the creation of this new button and adding it to this container, then, well, something could throw there, and then you'd have a leak. And then afterwards, when you move it, well, it's not obvious that the ownership is transferred. And there was actually also a second way to do it, and that's to create, to call this constructor directly with the container as a parameter. But the problem with that is we'd have to be really careful in the implementation of this add widget code because we couldn't assume that it was like a fully instantiated widget yet. So we actually definitely had a few bugs related to that. So yeah, it's also mentioned in effective C++ that you shouldn't call virtual functions during construction or destruction, and there were places where we were doing that and we had to eliminate that. So it was already very clear what we had to do with method number 2. We had to just scratch it. So now the question was, what do we do with this first way of doing things? First we thought maybe, well, we could just not transfer ownership. For example, you could use make unique to make this button and then add a non-owning pointer to this container. But then you'd also have to make sure that this button stays around as long as you need it. There are pros to this because, well, there's no longer this potential leak when you have an exception. And it's clear who owns it. You just made it and you didn't move it, so you still own it. But the cons are, well, what if this button gets deleted? What do we do? Do we remove it from the widget tree and then the button just disappears? And it's completely valid and it will compile and there's no undefined behavior and it's really annoying to debug. So if you let the pointer dangle, that would be undefined behavior, but at least there will be tools that allow us to check that. It's also a bit cumbersome because you have to make sure that this button has to stay around for long enough. And in the end, you just end up making this whole shadow hierarchy or something like that to make sure that it stays around for long enough. And even worse, well, in this particular case, we could, of course, make it so that it doesn't compile anymore in several ways. But if you had existing Witty3 code, and you would just call new instead of make unique, and then pass that in, then that would just leak everywhere. So from this, we concluded that, well, this parent owns child relationship, that is still a good way of doing it, but we should make it clear some other way. And we also thought, well, maybe we could use shared pointers for that. So, for example, you could just call make shared and then add this shared pointer, and then you have a shared pointer in the container widget and where you just created it. Of course, this again doesn't leak when there's an exception that throws, but the ownership relationship is less clear here, and you have to watch out for accidentally creating memory leaks. And one of the ways that you could do that is that if you would define a lambda and then accidentally capture this shared pointer, then you would just create a loop. And it's thread safe, but we don't actually need it to be thread safe, because in a W application, we only modify the widget tree in one thread at a time. So it's like an event-driven system that guarantees that. So the equivalent of shared pointers to break these loops would be to use weak pointers, but then you'd actually it's actually cumbersome to use because it has to be thread safe. You could also, of course, use raw pointers, but then or references, but then it gets a bit weird because you're using on the one side a shared pointer and then on the other side. So we just decided to just keep it the same, but make it more explicit. So we would just use make unique to make the widgets and then move them over to the container. And this works, but there's an error on the slides. I hope you can spot it, but I will get back to that later. So again, when there's an exception that doesn't leak anymore, it's clear who owns it now because there's moves happening. But the cons are, well, this is a little bit more verbose, and even worse, well, the widget is null after you move it. So when you're actually connecting this signal slots to that signal, then, well, button is null and text is null. So that's actually going to blow up. So a straightforward way to fix that would just be to move the add widget calls to the back, and then it would be fine again. So this was the most common problem we encountered when porting our examples over. I actually only found this, well, actually once someone told me about this a few weeks ago that this existed, but I was looking for some checker for it, but it was actually too late. But this is one of the ways that we could check use after move problems like that. You could use client ID, and then if you use run client ID.py, you can run it on your entire project. And we actually, before release of Witty4, still found 2 of those problems. So luckily that was before release, not after. But because it was a quite common pattern now that we were adding these widgets to the widget tree, but then we still kind of needed them, we ended up creating these templated overloads where we could pass in a specific kind of widget, and then it would move that widget, but it would also keep a raw pointer and return that so that you can still use that. And then the example becomes a bit simpler. So instead of having these moves or having to save it with a .get or something, you could just call add widget, and as argument, you just construct it in place, and then you get a raw pointer out of that. And then you can later use that raw pointer to just still connect some signals to slots, for example. And then there was just one problem that we still had to tackle, and that's, we were a bit paranoid about what if this widget that emits this signal outlives widgets that are used in this slot. And that's how we came up with observing pointers. We thought, well, we need some kind of weak pointer, but then for things that are not in a shared pointer, and we didn't need it to be thread safe. So this is an extremely simple implementation now. So we just made every widget inherit from wiki core observable, and then these observing, and it would just keep a vector of these observing pointers, and whenever it was deleted, then it would just invalidate all those observing pointers. And the expectation there is that we'll have 0 or very few observing pointers pointing to one observable. We noticed actually that for the most part, this ended up being unnecessary because for the most part, the way that our applications worked, this was an uncommon edge case. And because we don't want to really force a new concept on to our users, and if they're sure that, they're definitely not going to have these dangling pointers, then we didn't want to necessarily say you have to use it. So nowhere in our API we return it, nowhere in our API we request it. So, but you can use it if you want to, but it's usually unnecessary. So that's like the whole way that we changed our ownership model and how we made it more clear. And so another thing that we could do now is, because C++ 11 and beyond incorporates a lot of features that were first in Boost, we could scratch a lot of that and replace it with stuff that's now in the STL. Because we knew that these Boost headers slowed compilation times a lot, especially because you have a lot of headers that are just made to support older compilers and stuff, and we didn't need that. We just targeted C++ 11 now. And on Windows, we actually had to distribute a binary version of Boost with our binary build on Windows because it had to be binary compatible. So we wanted to kind of eliminate it from our header files. So these are some of the substitutions that we made. So we replaced Boost.Signals 2, which was previously how our signal slot system works, with our own implementation. And now our implementation actually also, because of periodic templates, you don't need std bind anymore to bind away a lot of extra rubbish. And we also, for example, instead of Boost ASIO, we can now switch between Boost ASIO or standalone ASIO. So that one was the final one that enabled us to completely remove Boost from the headers. And Boost State Time we replaced with Chrono and Howard Hinnan's new date library, which is excellent and is proposed for inclusion in the standard at some point. And I hope that it will get in at some point because, that's one dependency fewer then. And the results of doing this were actually quite nice. One of them was, Boost.Signals 2 had quite long stack traces. If you wanted to see, in a lambda function, where is this really being emitted, this signal? Then you'd have to go all the way down to frame 12 to find where it was being emitted. And actually, I'm not showing all of the code here yet, because there's so many templates substitutions going on there. I shortened all of the lines now. So in Wiki 4, it's a little bit shorter. It's still on frame 6, but these lines are shorter and more understandable now. And also, one of the effects is, now that we eliminated the boost includes, we could really speed up our compilation times. So this is on this example that I showed you. So it's mostly really showing this overhead. And now the preprocessed file size is just a fifth of what it was before. And compilation time has also gone down with a fifth. And also our Windows builds now have a much smaller installer because we don't have to include Boost. It's also a lot faster to install because, well, Boost has a lot of tiny header files, and for some reason that's really slow to unpack on Windows. And our installed size went down by, it's now 3 times smaller, less than 3 times smaller. So Witty is now basically on Windows BYOB, bring your own Boost, if you want to. You don't actually need, but you can use any version of Boost that you want. So to conclude, so this explicit ownership now is nice. It's not straightforward, really, to adapt our ownership model to it. I think we did an all right job, but if someone else has some other ideas on how that could be done, then I would love to hear it. The additions to the STL are now a great opportunity to remove a lot of weights, especially where we're using Boost in our headers, and really speed up compilation times. And well, Witty 4 was released last week, and sadly, we haven't heard much yet. We have heard people say that our compilation time has improved, and that was good, but we really still have to hear from our users to really know if it was successful. And you can get Witty 4 now at webtoolkit.eu if you want. And I still have a little bit of time for questions.
Can you show the last slide where you added the make unique things?
This one?
No, where you have add widget.
Oh, that one, yeah.
That one, yeah. One more. That one.
Okay.
Why didn't you make add widget also the constructing of the push button and W text? You could have saved the make unique there explicitly.
You repeat that?
Just push it down, the make add widget a template.
Yeah, I was thinking about that, and I floated that idea. One of the, like, if you don't know necessarily that we're really following these rules of a raw pointer is always non-owning, then it would be less obvious that you're moving it. But yeah, it's something that we might still add now.
Even on this slide with 2 things, it's a lot of duplication that should be factored away.
So 401, we'll have that.
I have sort of similar comments because I don't really see the need of exposing the fact that it's a memory, and I mean the pointer at all to the user. You could also use return the reference, basically.
Yeah, so you're saying that we should return a reference instead of a pointer here.
Yes.
Yeah. Well, yeah, that's. I wanted to also ask Koen about that, about why you chose a pointer instead of a reference in this case. So I'm actually not sure. So, no more questions? Okay, thank you.